All right, welcome to 5.6. We're going to go ahead and get into this. This is modeling with harmonic motion. Um, so the definition of harmonic motion refers to motion or phenomena that repeats itself at regular intervals. I've given you a couple of examples, like the daily cycle, sunrise, sunset. So the sun comes up, goes down, goes up, goes down. An oscillating mass on spring. Um, Something you would know a lot more of this would be like a car suspension. That's a mass on a spring, right? There's a little suspension right here. And as it goes up and down as you hit a bump, that eventually dies out by design. Alternating electric currents, if you get into that. Motions of sound, or water is sound waves, like if you drop a pebble, the water goes up and down and slowly evens out. And I want you to try to think of two on your own. Any two you'd like that you want to define, that's fine. So try to think of any two on your own. I'm going to think of two more for us, and two more is like your heartbeat. Your heartbeat has a very regular rhythm to it. If you actually look at um, the electrical impulses, you can see they go up and down in a very regular way. If you run or stuff, things change. But if you're just sitting, it's in a simple harmonic motion at least. And like another thing is like musical instruments. Like take a guitar. So like a guitar, string vibration. So that string vibration is what makes the sound waves because it's vibrating in harmonic motion, vibration. Okay, so string vibration. So these are two things of harmonic motion. So we're going to be focusing on simple harmonic motion. So something that looks more or less like this for our things. So we talked about amplitude before. Your book introduces omega, which is a little bit more standard than the K we've been using, right? And when you talk about sound, the Greek letter omega for angular frequency. Um, we've just been using that to find the period so far, but we're going to dive a little bit more into it. And T represents time. So here we have a period, which is 2 pi omega, which is the same as 2 pi k, right? And here we're going to have frequency, where it is omega over 2 pi, or k over 2 pi. Your book introduces omega here, so I'm going to use omega here. And then it kind of goes back and forth a little bit after this. They can kind of be used interchangeably, so don't worry about if you see omega or k. Just treat the function as you see it. All right, so let's get into some of this stuff. So we've done a lot of this before. So given some vibration on a spring, it's modeled by this. What is the amplitude, period, and frequency? So the new thing we're looking for here is frequency. So the amplitude is the absolute value of what's up front. So in this case, it's 10. So the amplitude is 10. Our period from before, our period, or capital P, depends on how you want to write it, but I'll write out period for now, is 2 pi and over omega. Our omega in this case is 4 pi. So here we're going to put in a 4 pi here. So it would be 2 pi divided by 4 pi. And that's just going to give us a half, okay? So our period is half. And that's just a half of whatever we're working at. If it's a mass on a spring, I assume it's a half second, okay? Here, we'll talk about our frequency. And our frequency here is omega divided by 2 pi. Again, our omega is in the same spot as k, and it basically is k. You can use them interchangeably. And so here we'll get 4 pi over, oops, I said 4 pi. 4 pi over 2 pi, and you get 2. And what this probably means is this 2, if we're going to put a thing on it, it's probably in hertz, Hz. And hertz is cycles per second. So cycles per second. And that's how many times um, you complete a full revolution in a second. So how many, whatever that periodic function looks like, it'll do 2 sets of that period in 1 second. And so that's what hertz are. All right, let's go to the next page. So let's look at a case of damped harmonic motions. Most harmonic oscillators out in the real world are damped just because energy gets lost over time in many different forms, most often friction. So damped harmonic motion means external forces, usually friction or other things, could be a lot of things, um, can cause the amplitude to decrease over time. Sometimes you put dampening on things on purpose. Um, and this is modeled by this. So this looks like a normal thing, except we here have this damping term or coefficient right here. This is the damping coefficient. And so notice here, we're going to strictly say C is positive. That made this coefficient here, this coefficient is negative, which means that E will go to 0 over time. This term will go to 0 slowly over time, okay? If you remember your negative exponents from 126, you notice that this should, if you graph this, this term right here by itself slowly goes down. So what happens is when you graph the harmonic oscillator, it slowly goes down like that, following this term. Okay, so the amplitude gets smaller and smaller and smaller over time. Okay, and so that's what we have here. Your book uses this K, and so I'm using this K here. I don't love that it's what it is, but that's what your book uses. We used K for omega before, so they kind of switch out the terms. Just make sure what's up front, that's an amplitude. This is the dampening coefficient, right? This is your omega, which will help you determine your period or your frequency. And so it's positions what matters, not what letter you call it. You can really use whatever letter you want. Okay, so here they're going to use K for initial amplitude. I wish they'd used a different letter, but that's just what they use. So that's what we're going to use here. And let's look at a vibrating violin string. So we're going to pluck the string about 0.5 centimeters from its rest position and release and allow it to vibrate. They've determined for this violin at least the damping the C for this to be 1.4. Suppose that the note produced is a pure G, which is 200 hertz for those who are really deep into music theory. Find the equation that describes the motion of the point at which the string is plucked. Okay, so let's look at this and let's break it down very slowly. Okay. All right, so the first thing we need to do is, while we write sine or cosine, let's figure out which one we want first. So here we're going to start at a release position. So we're going to start at our amplitude. Therefore, we're going to want cosine. So cosine. Let me just write here. We're going to have cosine. So we're going to have y equal to some k e to the minus ct cosine of omega t. And we're going to try to find that. And the reason we want cosine is that we start at the amplitude. We're starting at the amplitude. So that's what cosine does, starts the amplitude. Okay, let's see if we can figure out some of these other things. All right, so our K, or amplitude, let's just write it as amplitude, is 0.5 centimeters. So 0.5 centimeters, where did I just read that? Straight off of here. It is pulled from its above rest position. So that's its amplitude. That's where we're starting. All right. Here, what do I know? I know its frequency. I know the frequency is equal to 200 hertz. And we know that just from right here. The frequency is 200 hertz. From there, I can get what omega is. So remember, frequency is equal to omega over 2 pi. So omega would equal 2 pi times my frequency. So omega would equal 2 pi times 200. So omega here is 400. Oops, 400 pi. So we have what omega is. Okay. The damping coefficient is given to us, or the C as part of our damping coefficient, to be more precise in my wording. It's given to us is to be 1.4. And in that, here we have K, we have omega, and we have our C. So we can write this out. And that's all the problem askers do, is just write this out. So K here is 0.5. We have e raised to the negative 1.4. That's just given to us in the problem. Notice right here, 1.4. So here, it's just given to us in the problem. We have our cosine, because we started our amplitude. And then we have our omega, in this case, 400 pi t. And so that string vibrates very, very quickly. All right, let's talk about phase angle and phase difference. All right, so my notation is going to differ a little bit from the book here, and that is for clarity's sake. Okay? All right, so here, if you take a general sine function, you have this phase angle here, phi. Your book, just so you know, your book uses b for this phi, and then the normal phase shift or the horizontal shift is phi over this. And I find that super confusing. So we're going to use phi for here. But now when you see your homework for the 5.6 section, and so in this section, B here will be the phi. Now for clarity, for when I teach this in person or in my exams and everything, this phi here is its own thing for phase angle, just for clarity. Okay, so there's a difference between the book. Okay, so here we have phi. So here we have our amplitude like we did before, our omega, a t minus our angle. So this is my phase angle. Okay, a phase shift can be written just to represent what we usually do. So this is now the phase shift. So it's the angle divided by the phase angle divided by omega is the B, or phase shift, or horizontal shift. Okay. When two objects move in simple have simple harmonic motions and they have the same frequency, right, or the same omega, um, their relative positions to each other can be determined by the phase difference in angles. So here when you do phase difference, you look for angles. Okay. So the phase difference is given by the first angle minus the second angle. Just find the difference between these two. Okay. If their difference is a multiple of 2 pi, that means that means they're in phase, right? They're in phase. And if otherwise, we say they're out of phase. Note, the book is going to use the word phase to refer to phase angle, which is correct. But I'm going to try to use phase angle to make sure you know when I want you to find the angle, and phase shift when I want you to find the distance. Okay? So I'm going to try to make that distinction as clear as possible. And so we're going to go ahead and do this in this example. So let's look at finding the phase shift and the phase difference on objects of this. So let's give us 3 different simulations of harmonic motion. Okay. We want to find the amplitude, the period, the phase angle, and the phase shift, or the horizontal shift, as your book calls it, of this. So let's start right here with, so we have y1. So start with A. Let's do that. A. Okay. And so here, let's find our amplitude. The amplitude here is 10, right? You can just read it off here. There's the 10, so our amplitude is 10. Our period is 2 pi over k, or omega, as it is in this case. So here we have our omega, which is 3 here. So 2 pi over 3 doesn't really simplify from there, but just leave that. Our phase angle, and remember your book will just ask for phase in that case. What they mean is the phase angle is equal to pi over 6. Remember, you do switch the signs. Okay. And then the horizontal shift or the phase shift. So the phase shift or the horizontal shift, or just the shift as I've been calling it, is equal to, we pull out the pi, so let me do that real quick. Let me show you an example of where that is pulled out. So sine of the 3, so you pull out that omega here, so we're going to pull out this omega, so this would be t, and then 6 divided by, 1 over 6 divided by 3 is 1/18. Okay, so our phase shift here is pi over 18. All right, so find the phase difference between curve y1 and y2. So notice here they have the same beginning. The only thing that differs here is this angle. So we're going to find the difference of the two angles b. So I'm going to take pi over 2 minus pi over 6. And that's going to give me pi over 3, because this would be 3 pi over 6. And so that minus 1 give me 2 pi over 6, which is pi over 3. When you take a difference, just take the larger minus the smaller, so your number is positive. Okay. Are these two curves in phase? The answer is no. They're not in phase, not in phase. All right, let's do the next one. C. Now we're going to compare y1 and y3. So here we have the same, here we have the same. So now we're going to pay this pi over 6 and this minus 23 pi over 6. So here we have pi over 6 minus 23 pi over 6, or minus the minus 23 pi over 6. Remember to flip the sign. And that gives us 24 pi over 6, or 4 pi, or in other words, 2 times 2 pi. So it is that. So yes, these are in phase. Yes, these are in phase. These are in phase. Okay. All right, it says graph all three curves on the same axis. So let's do that. Group that is D. All right, so I'm going to graph all three of these on the same axis. So here, notice here we have it written like this. That makes it easier to graph. So again, how to graph this? We go up 10, we go down 10. This is a sine curve. We're going to start at pi over 18. We're going to add one period to that, which is 2 pi over 3. So 2 pi over 3 would be 12 pi over 18. So add pi over 18 plus 12 pi over 18 gives me 13 pi over 18. All I'm doing here, so we start here, we add a period, which is this. Here I'm going to multiply both top and bottom by 6. That gives me 12 pi over 18. Plus 1, which gives me 13 pi over 18. Half of that would be 6. So pi plus 6 pi over 18 would be 7 pi over 18. We add our quarter marks. All right, and then we can go ahead and graph this. It starts at 0. Here's this amplitude of the quarter mark. Oops. Let's try that again. This amplitude of the quarter mark comes back down. This is amplitude and hits here. So here's our first one. Let's go ahead, and we're going to call this one y1. This is y1. And in fact, this is also y3. I'll show you that in a minute. But let's do y2. y2, pi over 2. If I divide pi over 2 by 3, I get pi over 6. In fact, let me write y. This is y1. Let me write y2 here. So this would be 10 times sine of 3 t minus pi over 6 if I rewrite this by pulling out this 3. So I pull out this 3, I get pi over 6. So I start at pi over 6. I add 2 pi over 3. In this case, I just have to multiply top and bottom by 2. And so I get 4 pi over 6. So I'm going to put this right here, add the pi over 6 to it, and I get 5 pi over 6. And then here I will get pi over 2, and then it comes up, comes down, goes through, and goes like this. And so this here is y2. Now to show that y3 is indeed the same as this one, let's do this one more time. I'm going to grab this and say y3 here. y3 is equal to 10. Let's go back here. 10. Sine, let's pull out that 3, 10, and then divide by 6, so 23 pi over 6. Okay, so 23 pi over 6. All right, so that means, over 18, sorry. Oops, if I pull out that 3, over 18. So where would I start this? Well, I would start this way back here, right? I start this way over here at minus 23 pi 18ths. And then if I go one period, so let's do this. So I start at minus 23 pi 18ths. And then if I add one period over that, that's 2 pi over 3. Remember, our period is 2 pi over 3. And so if I do that, remember that was 12/16. So here I'm at, and that's equal to minus 11 pi over 18. And if I do that one more time, if I take 11 pi over 18, add one more period to it, 11 pi over 18, add another 2 pi over 3, or again, that is 12 pi, that's equal to pi over 8. And so that means that it's done 2 periods here, so it's gone up and down twice, and then it comes in here, oops, so it's going to come up and down twice, then comes in here, and then it exactly will match this one. And so these two are in phase. All right, and that's the end of the notes for this section.